our team tries to develop devices to investigate the nervous system, which encompasses many parts of the nervous system. We are fairly agnostic. We are interested in the function of the brain, but also we're interested in spinal cord as well as the peripheral nervous system. So if you're thinking about the brain, you're thinking about neurological disorders like, for example, Parkinson's disease or depression. And we are working to produce devices to study those really complicated disorders. And let me show you one of the fibers that was built to study brain circuits. So this is actually a preform of the fiber. It is so mother of the fiber essentially was going to get drawn down to the microscale, but on the macro scale it looks like this. So what we did here is we have a core that has an optical channel. It's going to become an optical fiber. We have conductive elements that will become electrodes, and we have hollow channels which will become microfluidics. So this device can then be drawn down to this scale. You can see something that you cannot actually see because it's about hair thin, but inside it all the same features remain. So exactly the same cross-section, but many times smaller. And now, using this device, we were able to modulate nervous system, brain circuits for the first time, optically, chemically, and electrically, all at the same time. And now, using that, you can study how these disorders really develop and how we can potentially use the same functional features to treat some of those emerging symptoms, because we'll be able to do it in real time. Similarly, we also work in the peripheral nervous system and in the spinal cord. Spinal cord, you can think of a fairly simple and really devastating condition. When somebody is in a car crash, their spinal cord is severed, now they're paralyzed neck down, the signals are not propagating from the brain to the extremities. So we are working to develop devices that will be able to bridge this gap across this severed spinal cord, and for that we need to support both the growth of the natural neural tissue. For this we can use our fibers essentially scaffolds, but we also need to stimulate signal transduction across this gap. So our device needs to be smart and still incorporate all those electrical and optical and microfluidic features. And an interesting thing about the spinal cord, it stretches. Unlike the brain, which moves a little bit every time you breathe in, but doesn't stretch by 12% or more as spinal cord. So for this type of application, we create fibers that also can stretch. For example, this device contains electrodes built of elastomeric composite, and it also has optical features, and you can see how it can withstand those stretching deformations. And we can now think about incorporating these types of materials into these scaffold type devices to be able to interface with the spinal cord.